Hey everyone, welcome back to our last lesson for this week. In this lesson, we're going to be talking about power and sample size through defining what power is, talking about type 1, type 2 error again, and then giving us an example on how we can compute sample size using JMP and RStudio. So, what is power? Power in hypothesis testing is the probability to detect a difference between the means when the difference is actually there. So that's going to fall into this decision table right here. And the decision is to either fail to reject H naught or reject H naught. This comes from our analysis with our p-values, which we've talked about in previous lessons. And we're going to compare it to whether the hypothesis is true, the null hypothesis is true or not. Okay, so if we fail to reject the null hypothesis and the null hypothesis is true, then we're making a correct decision. So this is a good thing. And the probability of that is 1 minus alpha, where alpha is our significance. And we've talked about this alpha in the previous lectures. It's typically set at 0.05, but that's not the end all be all. You could have 0.1 and whatnot. Now, if we reject the null hypothesis, reject the null, and the null is true, this is when we're going to make a type 1 error. So this is bad. Error. Another option is if we fail to reject the null when the null is false. So we fail to reject and it's false. This is going to be a type 2 error again. This isn't going to be good. And so when we should have favored the alternative, but we actually failed to reject the null. So this is when we should have said yes to the alternative, but we didn't. Okay, and then our last one is when we reject the null and the null is false. This is also a correct decision. And this is also what we call power. And power is going to be 1 minus beta, where beta is the probability of making a type 2 error. And so again, power is what we're going to be talking about today, and it's the ability to detect a difference when there is actually a difference. All right? So in order to talk about power, we have to talk about what's going to influence it. And so before we do that, I want to look at some graphics to help us demonstrate and understand the idea of power. So in your notes, I have these pictures, but what I'm going to go to is JMP. And JMP provides us with a great animation to help understand power a little bit more with these pictures moving. All right, before we go, I'm just going to talk about these labels because they'll be the exact same in JMP. So first, we're going to have this red distribution right here, which is going to be our hypothesis mean under kind of our null assumption. And then we have this blue mean distribution, which is the truth. So what we're trying to test, H naught mu less than or equal to 65, H A mu greater than 65. Okay, so this is what we want to test. This is our hypothesis, hypothesize, that's where the 65 is coming. And then our true, which again in practice we never really know the truth, but our true mean distribution is 68. So under the null hypotheses, we assume our red distribution is centered at 65. For a power and sample size scenario, we need to know what the true mean distribution is. And so again, we're here assuming that it's going to be bigger than 65 and we're centering at 68. So if we're doing this, we assume we have drawn data from we draw data assume we draw data from here. And if we get data above this red line or above, we're going to reject our null hypothesis. Again, this area right here is set with our alpha level of 0.05. Okay. However, if we're lower than the cutoff, so this blue area, or lower, we're going to have a type 2 error. Now, one thing is these tails kind of go down and there's still area under here. It was just hard to draw that in my picture. And so we would fail to reject the H naught when we should reject in this case. Because again, here's our truth. And if we were failing to reject, this is going to be a type 2 error. All right. And so there's going to be a lot of different, not a lot, but there's going to be several aspects that's going to affect this type 2 error and this alpha. More specifically, what we want to be looking at is this area right here. Because again, if we go back up to our formula, power is 1 minus beta. If this is our type 2, then our power is going to be all this yellow shaded. And so what we're going to look at in our jump animation is what's going to affect this yellow area and this blue area. Because as blue decreases, yellow is going to increase. And as blue increases, yellow is going to decrease. All right, so let's go to jump and talk a little bit more. So the weird thing about jump in this animation is they're going to give you this estimated mean right here. But that doesn't matter because the idea with power is you're going to do a power / sample size calibration before you actually collect the data. So you are figuring out the power of your test and your sample size, so we don't really have data to estimate the mean yet. Again, here is our hypothesized mean, is this red distribution, and our true mean is the blue. This blue area right here, the shaded blue, is going to represent our type 2 error, and this red area is representing our alpha of 0.05. Now, the chances of being in this blue area are pretty low, because if you look at the true distribution, where it's centered at 68, then the bulk of the distribution is going to be over here, whereas the tail has a lot less of the area, and so our type 2 error is going to be small. And we see that right here with this beta is small. And what's being impacted here, and one of the things that impacts power, is how big the difference we want to detect. So if I was to take this null distribution, and let's say we make it further away, so the difference between these two distributions is getting larger and larger and larger. We can notice that our beta is getting super small and we pretty much don't even see the shaded area anymore. And so what we're seeing is power is going to 1, and so it's going to be easy to detect this right here. However, if we took our distributions and we put them really close to each other, notice how this beta is increasing. Again, that's the blue shaded area, and our power is decreasing. So it's going to be harder to detect a difference when our hypothesized mean and our true mean are close together. Now, if I was to bring this back a little bit more away, another thing that will impact our type 2 error and our power is going to be what we pick as our alpha. So again, this red shaded is our alpha. And if we came here and let's say we increased it, we're going to notice a change in our type 2 error. So we noticed that this cutoff point moved to the left and we got a smaller beta and our power increased. Notice these two numbers do sum up to 1. Now, if we go back to our 0.5, the other thing that's going to affect power is our sample size. So right now we have a sample size of 40, but if we were to increase this to maybe, let's say 50, it's going to change and increase our power as well. So all of this relates back to these pictures, where here is when the differences are super far apart, here's when they're close, and then here is when alpha is 0.10. But more specifically, this is going to relate back to what's really going to impact our power and sample size calculation. Since we're talking about a completely randomized design, this is a one-way ANOVA sample size calculation, so we can think of our sample size as the replicates in one-way ANOVA. A frequent question that we see a lot in design experiments is how many replicates should I use? And we can figure this out with using power, okay? So again, let's just recap that if we increase our number of replicates, we're going to increase our power. We showed that with the animation. To determine our number of replicates, we're going to have to look at a couple different things. First, we're going to have to look at our desired power, so 1 minus beta. And typically what I've seen, it's been set to 0.8 or 8% power, 80% power. And so if power increases, the sample size increases. If power decreases, then the sample size won't be as high. And this is an input. I would recommend going to your literature. Every literature and every field is different, and that would probably give you a better understanding of what your field deems acceptable. Another thing, again, is the significance level. This is typically set to 0.05, but it doesn't always have to be. Again, I would check your literature to make sure you're doing things that your journals that you're applying to or submitting to will accept it. Another thing is the effect size. The effect size is, if we think back to the red and blue distribution, it's the distance between those distributions. The effect size is the size of the difference that we want to be able to detect. So we saw as the difference decreased between the two distributions, the power decreased. And as the difference increased, the power increased. This is also a hard decision. Some studies would use a rough rule that 1 standard deviation of change in the mean would be important. Again, I would look at some of your literature within your field to help figure out what is a good effect size for your case study. Another thing that's a little bit hard is trying to assess the natural variation, so sigma. This estimate can be attained a couple different ways. One is through a pilot study. So maybe you did a small study and kind of figured out some information, or you can use some prior knowledge or a lit review in which they give you their squared MSE. Or there's a less scientific approach, which is using the range of the data for a given treatment and dividing it by 4. Some intuition behind this is that if we think back to the empirical rule states that 95% of our data should be within 2 standard deviations in the mean, which spans over 4. So let me just draw a quick picture. Use black. So if we had here was our mean. Our empirical rule had 1 standard deviation from it, and then we had minus 2 standard deviations plus 2 standard deviations. This is supposed to have 95% of the data. And so 1, 2, 3, 4. That's where 4 is coming in from. And so to get 1 standard deviation, we divide by 4. We don't divide by 6 because with 6 standard deviations, we would have 99% of the data, and this is going to lower our variance estimate. And so with 4, we're being a little bit more conservative, and this part would be the last resort. I would try to go find a pilot study, prior knowledge, or a lit review before doing this case. That being said, we are going to use it in this example. For your homework, as a hint, you're going to be doing it through a pilot study. So problem 1 in your homework, you're going to be doing an ANOVA, you're going to do contrast, multiple comparisons. And problem 2, I'm going to ask you all to do a power sample size calculation in which you're going to have a pilot study, and your pilot study is from problem 1, in which you're going to grab the square root of the MSE and plug it into your calculation. Let's get to an example so we can hopefully do our homework. So a researcher is designing a project to study the yield of pecans under 4 rates of nitrogen. The researcher knows that if the average pecan yields different by more than 15 pounds, there is an advantage in using the treatment providing the higher yield. Thus, the researcher wants to determine the necessary replications to be 90% certain that the F-test will reject H0 and hence detect a difference in the average yields between the nitrogen rates, differing by more than 15 pounds. The test must have a significance of 0.05. So let's try to pull out all the important information from this so that we can do figure out our number of replicates. Our desired power is coming from this statement right here. So we know we want power to be 0.9. Our alpha rate's coming from, we're told. Our effect size, a minimum significant distance of 15, is coming from here and up there technically. The only thing we don't have is the assessment of sigma. So I'm going to tell you. From a previous study, researchers know that the yield of this data ranges from 40 to 70. And so we're going to use our heuristic type rule to say our sigma is going to be 7.5. And so typically what I would do is show you the steps by hand as I did with ANOVA, and then send y'all to JUMP or R to do the calculation and show you how we do it. But here's the thing is, for power and sample size calculation, we don't do it by hand. So to show you and help us understand the different parts, I'm going to jump over to JUMP and demonstrate some of these pictures and what they're meaning. Okay. So in JUMP or R or other softwares, you kind of have to put in your mean values for the treatments. The reason for this is the case in that those mean values will tell our software how many groups you have. And so again, in this case, our researchers are interested in a change of 15 and we have 4 groups. The hardest situation to detect if 2 groups differ by a specific difference is when those 2 groups differ and then the remaining groups are centered in the middle of those. And so with our example, what we're going to do is we're going to have, again, we're trying to detect if there's a difference of 15. We're going to set mu1 to 0, mu2 to 15, and then we're going to put mu3 and 4 right in the middle. This should be an equal sign, because if you take the average of these 2, this is going to be in the middle. And then if we had a 5th group, again, we can put our mu5 right in the middle.
All right, so let's talk about how we can do this in JUMP as well as some of the results. If you're going to use R, I recommend still watching this video because I'm going to be talking about most of the points here, and then I'll briefly talk about the difference between JUMP and R in the inputs. So you're going to go to DOE, Design Diagnostics, Sample Size and Power. You're going to click on K sample means, and then here we're going to have our standard deviation of 7.5 as our natural variance. We're going to have 0, 15, 7.5, 7.5. Now we also want a power of 0.90, and then all we're going to do is click continue, and we're going to get a sample size here of 33. Now in JUMP, this sample size is going to represent the total sample size, and so to get the number of replicates per group, you want to take 33 and divide it by 4, which will get you roughly 8.25, And so we would round up to about 9 replications per each group. So that's how we use power to find our sample size. Now, let's say we have 9 replicates in each group, and we want to figure out what the actual power would be for this example. And so we would get rid of power, and then 9 times 4 is 36, so we have 36 total samples, and we're going to press continue, and we can see we have a power of 93%. Now, y'all might tell me, well, my data doesn't go from 0 to 15, and this doesn't represent the range of my data. So let me show you that it doesn't matter, the scale doesn't matter. So if we went 15 so our difference still is 15, and we're putting the other groups in the middle because this is the hardest case to detect. We can now go back to 0.90 and get rid of our sample size because this is what we're going to look at. And we can see that we still get 33. Again, just as another demo, get rid of sample size, get rid of sample size, and would still get 33. So the scale doesn't matter. So typically doing 0, 15, or whatever your difference may be, if you want your difference to be 20, you put 20 here, and then the middle point, and run it that way. The last thing that I want to bring up is our standard deviation. So let's say we increased our standard deviation, and we're still looking at the same power, and we press continue. We're going to notice that our sample size went up. So as our standard deviation or our variance increases, we're going to need more samples to be able to detect a difference.
Here's example 2, example 3, and 4. Key note is this is sigma you're inputting in JMP. And so this would be equal to the square root of your MSE. This MSE could come from an ANOVA table. Scroll that up a bit. The reason I point that out, and to remind you, the sample size in JMP is the total sample size. And if you want per group, it's going to be n divided by your number of groups. They use K for their number of groups. We used T for number of treatments. They also use little n for their big sample size, and we use big N. So in our notation, it would probably be n over T is going to be our number of reps, which should look familiar from lesson 1. Here's the one thing that I want you guys to notice more about the difference in software. So I also have R code here, and with R set up a little bit differently. The thing I want to let y'all notice first is that this with invariance for R, it's variance. And so we're plugging in sigma squared for R. That's a big difference between JMP and R. All right. These other little details I'll talk more about in the R video. But one big difference is that JMP wants you to put in the variance. No, JMP wants you to put in the standard deviation, and R wants to put you in the variance. Another large difference is that here's the output for R. Again, if you're an R user, I'll talk more about this in the R video. But again, you'll notice that the results are the same in the different groups. But what is it, again, is it's outputting the variance. So if you took 7.5 squared it, you'd get 56.2. That's where that's coming from. And what R is outputting is the number in each group. So notice we get 8.13, where in JMP, we got 33. Okay, so that is just a big difference. This is more of a caution of when you're switching between softwares, always, always, always Google or help file what's being inputted and what's being outputted so you don't get mixed up. That's going to conclude this week's lessons.